Now that we've seen how to describe the graphs, or at least certain properties of graphs of polynomial functions, the next type of function that we want to consider are rational functions. So a rational function is of the form f of x equals p of x over q of x, where p and q are polynomial functions. So they are functions that can be described using formulas that are rational expressions, that is, one polynomial over another one. Now, we've looked at polynomial or expressions and rational expressions before, and some of the things that we looked at there are also going to apply here. However, when we go to talk about the graphs of these types of functions, we'll have some new things to consider. As it turns out, the graphs of rational functions can be fairly complicated compared to the graphs of polynomial functions. The first thing that I want to remind us of, though, is how to find the domain and the intercepts of a rational function. These we can find purely algebraically, and we don't need to know how to describe these on the graph. And however, they are essential components of graphing the function once we get to it. So let's recall a few things for how to do this. So to find the domain of a rational function f, you set q of x equal to 0 and then remove any solutions from the domain. The thing that can sort of go wrong when we're looking at a rational function is if the denominator of the function winds up being 0. If the denominator of the function can ever be 0, then the inputs that make that happen can't be in the domain of the function, because the domain of the function can't include any numbers that would make the output undefined, which is what would happen if the denominator were 0. So this is how we find the domain of f. We set the denominator equal to 0 and eliminate any solutions to that equation. Now, to find the x-intercepts of f, these will be numbers where when we plug it into the function f, we get 0 out of it. Now, the fact is that when we're looking at a fraction like this, the only way for a fraction to be 0 is if the numerator is 0. So if the numerator is 0 and the denominator isn't, then the whole fraction is 0. But if the numerator is not 0, then there's no way for the fraction to be 0. So in other words, the function is going to have an output of 0 if and only if the numerator is 0 and the denominator isn't. So we're only going to be looking at values here that are in the domain, of course. So to find the x-intercepts of f, we're going to set p of x equal to 0 and then find the solutions. And those are going to be the x-coordinates of the x-intercepts. And then to find the y-intercepts of f, we simply evaluate f of 0. And that gives us the y value of the y-intercept. So let's see an example where we just find the domain x-intercepts and y-intercepts of a function before we move on to figure out what its actual graph looks like. All right, so let's find the domain x-intercepts and and y-intercepts of the function f of x equals x squared minus 4 over x squared plus, we want 7x plus 12. So, when we are looking at a function like this, we want to find the domain, the x-intercepts, and the y-intercepts. We're going to need to know where the numerator and the denominator are 0. Now, it turns out that the best way to do that is typically going to be to factor the numerator and denominator. However, for things that we're going to see in a moment, we're going to want to factor the numerator and denominator for other reasons as well. So usually when you're working with a rational function, the best thing to do is to just start your whole process by factoring the numerator and denominator if possible. So we start by factoring the top and bottom. And so we get f of x is equal to x squared minus 4 over x squared plus 7x plus 12. Now, both the numerator and denominator here can factor. X squared minus 4 is a difference of squares and factors as x plus 2 times x minus 2. X squared plus 7x plus 12 can factor. We want two numbers that add to equal 7, multiply to equal 12. Well, 3 and 4 will do that. So we get x plus 2 times x minus 2 over x plus 3 times x plus 4. And the thing to remember is that the numerator determines the x-intercepts of the function, or also known as the zeros of the function. The denominator determines the domain of the function, as well as some other properties of the graph that we'll look into in a second. So let's find the domain first. So for the domain, what we want to do is we want to set the denominator in its factored form equal to 0 and solve it. And we've done this many times by now. If x plus 3 times x plus 4 equals 0, that means that x plus 3 equals 0 or x plus 4 equals 0, from which we can conclude that x equals negative 3 or x equals negative 4. So this tells us that the domain of the function is the set of all numbers x such that x is not equal to negative 3 or negative 4. We can also write it in interval notation as the interval from negative infinity to negative 3, union the interval from negative 3 to 4, union the interval from negative 4 to infinity. So all real numbers except negative 3 and negative 4. So that gives us our domain. Let's find our x-intercepts. For our x-intercepts, we'll take the numerator and set it equal to 0. And that tells us that x plus 2 equals 0 or x minus 2 equals 0, which gives us x is equal to negative 2 or x is equal to 2. So our x-intercepts occur at the numbers negative 2, 0 and 2, 0. Finally, for our y-intercept, we simply have to plug 0 into the function. So f of 0, and this we can use either the factored form or the non-factored form. Which one you use is mostly a matter of personal preference. I'll go ahead and use the original this time. So we get 0 squared minus 4 over 0 squared plus 7 times 0 plus 12, which gives us negative 4 over 12, which simplifies to negative 1/3. So that tells us that the y-intercept of this function is at 0, negative 1/3. We'll go ahead and refer back to this data a little bit later when we go to graph this, once we've looked at some of the other things that we can figure out about the graph based on the function. One of the main characteristics of the graphs of rational functions that are different from those of polynomial functions is the existence of asymptotes. Now, this is a fancy word from the Greek, and we can see examples of asymptotes when we look at the graph of one of our basic rational functions, y equals 1 over x. Now this is a graph, once we have it, that you should put in your toolbox, in your library of functions that you recognize, going along with linear functions and the parabolas for y equals x squared and absolute values, things like this. Y equals 1 over x is another one of these. It's sort of our basic rational function. Now, in order to see what the graph of y equals 1 over x looks like, let's go ahead and plot some points. So let's take this grid and put it here. And so yeah, let's just plot some points. Let's take some x values, take some, and get the y values that go along with that. Y is 1 over x. Now, the first thing to note is that when x is 0, y is undefined. This is going to wind up being important to us later on. Notice that 0 is a point that's not in the domain of the function defined by y equals 1 over x. That's going to be important for what we do later. So let's choose some values of x. If x is 1, then y is 1 over 1, which is 1. If x is 2, then y is 1 over 2. If x is 3, then y is 1 over 3, so forth. But let's also look at some fractions. This 1 over x, this is called the reciprocal function. And to see why that is, let's look at what happens when we plug in 1/2. If we plug 1/2 into the function y equals 1 over x, then we'll get y equals 1 over 1/2. Now remember that dividing by a fraction the way that we've done here is the same as multiplying by its reciprocal. So if we take 1 divided by 1/2, that's the same as taking 1 times 2 over 1. This is the flip and multiply strategy for simplifying complex fractions. And this whole thing simplifies down to just 2. So when x is 1/2, y is 2. When x is 1/3, similarly, y is 3. So this function 1 over x is the reciprocal function. It takes a number and gives back its reciprocal. So let's try plotting these. Now let's set it up like this. I'll make every 3 squares along here a unit. And let's plot some of these points. So when x is 0, y is undefined. When x is 1, y is 1. When x is 2, y is 1/2. And when x is 3, y is 1/3. When x is 1/2, y is 2. So that gives us the point up here. And when x is 1/3, y is 3. So here are the various points that we found that are on the graph of y equals 1 over x. Now, if we also plug in the negatives of these, we'll see that of these x values, we get the negatives of the y's as well. So, in fact, this function is symmetric about the origin, and by plugging these in, we get similar points reflected around the origin over on the other side of the graph. So here are the points that we got for the graph of y equals 1 over x, and if we connect them all up smoothly, then we get a graph that looks something like this. And we get a similar thing going on here. As we move off to the left. So, there are a few things to note about this. First of all, this graph, unlike any of the graphs that we've seen, well, other than the piecewise defined graphs, has two different components to it. You've got the branch on the upper right quadrant of the graph and a branch on the lower left quadrant of the graph, and they don't connect to one another. If we think about what happens to the values of this function as the values of x keep getting closer and closer to 0, then what's happening is that the y values on this graph are the reciprocals of these smaller and smaller values. So if we look at the x value of, say, 1/100th here, then the y value corresponding to that will be at a y value of 100. So the point 1/100th comma 100 is on the graph of the function. And in fact, as you make your x values smaller, as you move closer and closer to 0 along the x-axis, you wind up getting larger and larger y values. This is an example of what we call a vertical asymptote. We'll define it in a second, but this is the picture to keep in mind about it. So a vertical asymptote, intuitively, is a vertical line that the graph of the function gets closer and closer to, but doesn't actually touch, that where the graph keeps going up and up and up and up without bound as it gets closer and closer to that vertical line. So we would say that this function has a vertical asymptote at x equals 0. So it's a vertical line. It's not actually part of the graph, but it's something that describes how the graph behaves when you move closer and closer to it on the x values, when the inputs get closer and closer to the x value of this vertical line. Then if we look at what happens to the far left and the far right, if we start asking about the end behavior of this function, we see a similar thing happening. We see that as we move further and further, further and further to the right or further and further to the left, that the graph of the function is going to get closer and closer to this horizontal line, which we call a horizontal asymptote at y equals 0. In this case, y equals 0 is the equation of the green line, which is the horizontal asymptote of this function. So these are ways that we have of describing what the graph of rational functions look like that don't appear on polynomial functions. Now, I should point out that a rational function might have no vertical asymptotes, might have one, it might have many vertical asymptotes. And similarly, it might not have a horizontal asymptote. It might have one horizontal asymptote, although it actually can't have more than one horizontal asymptote. We'll summarize this right now as we go to define it. So our definition, the line x equals 0, x equals a, I should say, because we're going to talk about an arbitrary asymptote. So we'll take a line here x equals a. The line x equals a is a vertical asymptote if, as x goes to a, that is, as x gets closer to a, f of x goes to positive or negative infinity. That is, f of x grows without bound in the positive or negative direction. So a vertical asymptote will have a graph that near it looks, or might look like this. So it might go up when you're on the left side of the asymptote and go down when you're on the right side of the asymptote, as sketched here. Might be vice versa, as we did before. It can also look in a couple of other ways. Let me sketch out a couple of possible ways that we can have the asymptote. It can also be the case that the graph goes upwards, goes up towards infinity on both sides of the asymptote, or it could be that it goes down towards negative infinity on both sides of the asymptote. All of these types of behaviors are possible, and we'll talk in a moment about how we can determine which kind it is. Now, talking about horizontal asymptotes, the line y equals b is a horizontal asymptote if, as x goes to plus or minus infinity, that is, we're basically looking at the end behavior, as x goes to plus or minus infinity, f of x goes to b. So this would be a situation like the following. We've got a line y equals b, and then we've got function. The function gets closer and closer to this line as you move off to the left or the right. Now, there are several ways that this can happen. It can approach it from one side, sort of just like a rotated version of what a vertical asymptote looks like. But it can also do something where it comes down and back up and goes through there. It's sometimes said that a function can't touch its asymptote. And in fact, even the word asymptote comes from the Greek meaning not touching, but that actually only applies to vertical asymptotes. A rational function will not cross its vertical asymptotes, but it may cross its horizontal asymptotes, as in the cartoon example that we've got here, where the red graph does in fact cross the green line. So these are what horizontal and vertical asymptotes look like. Let's look at how we can take the expression of a function and determine where the asymptotes are, and if we can, what type of behavior occurs there in terms of these various types of patterns of the function. All right, so here's the fact that we're going to use. Vertical asymptotes are determined by the factors of the denominator of the rational function f of x. Importantly, though, this is after reducing. That is, after simplifying. So, so more precisely, if we write f of x as some numerator p of x, and we don't have to worry much about this, and then we've got our denominator x minus b1 to the m1. Actually, I want to be consistent with what we do next. x1 minus b1 to the n1, xk minus bk to the nk. If we factored our denominator into a bunch of different factors with these powers, which reminds us of our of how we were looking at multiplicity, and none of the numbers b1, b2, etc. up to bk are zeros of the polynomial p, then this means that f has vertical asymptotes. As vertical asymptotes of, I should say, x equals b1, x equals b2, up through x equals bk. Now, the numbers n up above also tell us something about the asymptotes. They tell us whether the function goes in the same or the opposite directions when you look on either side of the asymptote. If one of these ni's is odd, then the asymptote x equals bi looks like one of the following. We either have, just let me do that right. We either have that the function goes up on the left side of the asymptote and down on the right side of the asymptote, or, sorry about that, we have that it goes opposite that, it goes down on the left and up on the right. So if the power of the factor x minus bi, which is giving you the asymptote at bi, is odd, then the function goes in two opposite directions when you are close to the asymptote. And then if the ni is even, the asymptote x equals bi looks like one of the following. It'll either have the function going up towards infinity on both sides of the asymptote, or it'll have the function going down towards negative infinity on, that wasn't very good, on both sides of the asymptote. So the powers of the factors giving you the asymptotes work similarly to how the zeros of the polynomial p determine the multiplicity of the zeros of p. And in fact, there is a duality here, and advanced mathematics will study this in quite a bit of detail. But for us, we just care that the pattern that we see here does matter. The evenness or oddness of powers of factors tends to have a great deal of power over how the function behaves near whatever sort of point that that term is describing. I should also note at this point that when we're finding the zeros of the rational function, then the powers also matter there, which we will come back to and address in a moment. For now, let's just do a couple of examples of looking at these vertical asymptotes. And in particular, we'll talk about this important statement right here after reducing. So let's find the vertical asymptotes of f of x equals 2 over x minus 3. Now this is a very simple rational function. It's just a constant over a linear term. In this case, the denominator is entirely factored, so our answer, we just have the single factor of x minus 3 in the denominator, and therefore so since x minus 3 is the denominator, the asymptote of f is x equals 3. So when we go to graph out this function, we will graph the vertical line x equals 3, and we know that the function f has an asymptote, has that line as an asymptote. Furthermore, we know that the function will go in opposite directions when it's close to the asymptote, although at this point we don't know exactly which way it's going to go. Let's do some other examples. Let's do f of x equals x squared plus 1. X squared minus 1 is what I meant there, over x squared plus 2x plus 1. Now here, and we're doing the same thing, finding the vertical asymptotes. Now here, the first thing to do is to factor everything. We didn't have to the first time because everything was already factored. Here we do. So we'll factor the numerator and we'll factor the denominator. And in this case, this is what the factors look like. Now here, you'll notice that there's a common factor that appears in both the numerator and the denominator. The factor x plus 1 appears in both. And when that happens, before determining the zeros of the function and before determining the vertical asymptotes of the function, you have to cancel any common factors. So we must cancel common factors before finding the vertical asymptotes or zeros, that is x-intercepts, but we have to find the domain. If we need to find the domain, we have to find the domain before canceling. So when working with a function, a rational function, and you want to find out all these things about it, you'll want to start by factoring it completely. Then you find the domain. It's only after you determine the domain that you cancel things, reduce things, and only then you go to find the vertical asymptotes or the zeros. In a little bit, we'll write down a full list of the steps that you should take in order for working out what the graph of a rational function looks like. So for us, we'll cancel these x plus 1s because we're only interested in the vertical asymptotes. And so we have that this equals the function x minus 1 over x plus 1. And now we can see that this factor in the denominator, the only factor left, determines the asymptotes, and this tells us that we have a vertical asymptote at x equals negative 1. Let's do one more example. Let's do f of x equals x squared plus 5x plus 4 over x squared minus 6x plus 8. And again, first thing we want to do is factor this. This happens to factor as x plus 4 times x plus 1 over x minus 4 times x minus 2. Now at this point, we would want to reduce it if there were any common factors. In this case, there aren't. So this is the reduced form of the rational function f, and so we can look at the denominator to find our asymptotes. Now in this case, we have two vertical asymptotes. So we've got a vertical asymptote, which I will from now on abbreviate as VA usually. We have a vertical asymptote at x equals 4 and a vertical asymptote of x equals 2. So this is how we determine the vertical asymptotes of a function. Let's take one more example. If we have f of x is equal to 3x squared over x squared plus 1, then the numerator is actually completely factored, and so is the denominator. The expression x squared plus 1 doesn't factor. Furthermore, the equation x squared plus 1 equals 0 has no solutions. And so this means that, in fact, the denominator of this function is never equal to 0, which means, well, for one thing, its domain is all real numbers, but in particular, this means that f has no vertical asymptotes. All right, and then one final example. Let's look at f of x equals 2x plus 1 over x squared plus x plus 1. Now, this one we've got to be a little bit careful of. So we first check to see whether we can factor things, and it doesn't appear that we can. We don't have any of our normal factoring techniques that will work on our denominator. The numerator is already factored. However, if there is a 0 of the denominator, it can still give us a vertical asymptote. And sometimes we have to get at that using things like the quadratic formula. So, to find vertical asymptotes, we find where the denominator is 0. Now this is the same as the pattern that we described before if we can factor it, but even when we can't, then places where the denominator is 0 can give us vertical asymptotes, but I should specify here is that we need to find where the denominator is 0, but the numerator isn't. If we can find places where the denominator is 0, but the numerator isn't 0, then we have a vertical asymptote there. If we have some place where the denominator and numerator are both 0, then it's unclear. We won't be able to say what goes on there. Let me summarize this in a second once we've finished our once we finish this example. So we want to find out where the denominator x squared plus x plus 1 equals 0. As I said, we can't factor this. This doesn't factor by our normal techniques, so we'll use the quadratic formula. So this means that x is equal to, and then we'll use it, negative b, and b is 1 here, plus or minus the square root of b squared minus 4 times a is c here, 1, c is 1 here, all over 2 times 1. And this gives us x is equal to negative 1 plus or minus the square root of negative 3 over 2. And again, we see that the denominator has no asymptotes because this has no real solutions because of that negative 3 in the square root. So sometimes we go here and we can find out that there are no asymptotes. However, let's change this problem just slightly and see what happens. If we make the denominator x squared plus x minus 1 instead of x squared plus x plus 1, then that changes this c in the quadratic formula to a negative 1, which means that at this case, at this point down here, we would actually wind up with 5. So we get negative 1 plus or minus the square root of 5 over 2. Now, this means that we have potential asymptotes at x equals negative 1 plus the square root of 5 over 2 and x equals negative 1 minus the square root of 5 over 2. We can know that they are actual asymptotes, not just potential ones, by seeing whether either of them make the numerator 0. But the only value of x making the numerator 0 is negative 1/2. If we set the numerator equal to 0 and solve for x, we get negative 1/2. And so neither of our potential asymptotes are equal to negative 1/2, and so neither of them make the numerator 0. So they are asymptotes. So in this case, our function has a couple of asymptotes. X equals negative 1 plus the square root of 5 over 2, and x equals negative 1 minus the square root of 5 over 2. So a couple of irrational numbers, but they are perfectly good numbers where a function might have an asymptote. So now let's talk about finding the horizontal asymptotes of a rational function. And actually, this is much easier than finding the vertical asymptotes. It's something that we can usually read straight off of the function in its original state even before it's factored. So, to find the horizontal asymptote, if one exists, we want to compare the degrees of the numerator and denominator. So, before we get to the conclusion, I want to look at a few examples to see if we can sort of make sense of what happens. Now, a horizontal asymptote is describing what's happening to the y values of the function when x gets very, very large in either the positive or the negative direction. So we ask the question, as x goes to infinity, what happens to the function f of x equals 1 over x squared plus 3. So this is an example of a rational function. Now, in this case, the numerator is just 1, and the denominator is x squared plus 3. So let's ask what happens as x goes off to the right side of the graph, as x goes off towards infinity. Let's just try plugging in a few values of x in order to see if we can get a sense of what's going on. So let's try plugging in some values. If we plug 10 in, then we get 1 over 10 squared plus 3, which is 1 over 103. And if we plugged in 100, we get 1 over 100 squared plus 3, which is 1 over 1 over 10,003. And if we plugged in f of 1,000, we get 1 over 1,000 squared plus 3, which is 1 over 1,000,003. Now let's look at what's happening to these numbers as x is getting bigger and bigger. We're taking a fraction in each case. The numerator is 1 in all of these cases, but the denominator is getting bigger and bigger. We get 1 over 103, 1 over 10,003, 1 over 1,000,003, and these numbers, the full fraction numbers, are getting smaller and smaller and smaller. And in fact, if we wanted to make the output as small as possible, we could, or as small as we liked, we could just by taking x to be larger and larger. So we can say that in this case, as x goes to infinity, f of x looks like it's going to 0. Or in other words, the y values of the graph of f are close to 0 when x is very, very large. A similar thing is going to happen if we start plugging in negative values. In this case, we're actually going to get exactly the same numbers back because this happens to be an even function. But if we plug in negative 10, negative 100, negative 1,000, we're still going to be getting these numbers that are very close to 0. And this sort of behavior is going to apply whenever the degree of the denominator is higher than the degree of the numerator, when the degree on the bottom is greater than the degree on the top. So let's look at a slightly more complicated example. Let's look at the function x squared plus 2x minus 1 over x cubed plus 4x plus 3. And ask about what happens when x gets really, really big. What happens to f of x? So we can use some of the same analysis that we did last time, actually. When x is very, very big, f of x, which is x squared plus 2x minus 1 over x cubed plus 4x plus 3, is approximately equal to just x squared over x cubed. And this is because when x is very, very large, then x squared is much bigger than 2x or negative 1. And from a relative standpoint, the 2x and the negative 1 are going to matter a whole lot less than the x squared. Similarly, in the denominator, the x cubed term is going to dominate the other two terms from a relative standpoint. Now that means that when x is very, very large, the function f is approximately just x squared over x cubed, which is 1 over x. And now If x gets really, really big, then 1 over x gets very, very small. So if x is going to 10, 100, 1,000, 1 over x is going to 1 over 10, 1 over 100, 1 over 1,000, getting very, very, very small. So in fact, this gets very close to 0 as when x is very, very large. So we can say that as x goes to infinity, f of x goes to 0. And a similar result is going to apply if x is going towards negative infinity. F of x is going to go to 0. And in fact, this is going to apply whenever you have a rational function where the degree of the denominator is greater than the degree of the numerator. And in this case, we say that f has a horizontal asymptote of y equals 0. Whatever the function f does, and it might do lots of complicated things, but whatever it does, when x gets very, very large, the function graph, which might do lots of different stuff over here, will eventually get close to the graph of y equals 0. So this is what happens when the degree of the denominator is larger. Let's consider what happens when the degree of the denominator is equal to the degree of the numerator. So let's look at the example. F of x is equal to 3x to the fourth plus x squared plus 1 over 2x x to the fourth, plus x cubed plus 7. So again, we want to ask what happens to this function when x gets very, very large to the left or the right. What's its end behavior? So let's do the same thing. When x is very, very large, f of x, which is 3x to the fourth plus x squared plus 1 over 2x to the fourth plus x cubed plus 7 is approximately equal to, and again, the leading terms of these two polynomials are going to dominate the others. So the 3x to the fourth term is going to dominate the x squared in the 1 term. 2x to the fourth is going to dominate the x cubed in the 7. And so the terms with highest degrees are just going to overwhelm all of the others. And so when x is very, very large, f of x is approximately equal to 3x to the fourth over 2x to the fourth. But we can reduce this. We have an x to the fourth in the numerator and the denominator, and we just get 3 halves out of it. So, in fact, what this is saying is that when x gets very, very large in the positive direction or the negative direction, the same argument applies, then if we take the line y equals 3 halves, this function is going to, whatever else it does, get closer and closer to the horizontal asymptote at y equals 3 halves. And that's how we can calculate the horizontal asymptote of a function where the numerator and denominator have the same degree. What we do is we look at the ratio of the leading coefficients. We'll summarize all of this in a moment. We look at the ratio of the leading coefficients, and that will give us the y value of the horizontal asymptote for that rational function. Now, as it turns out, if the degree of the numerator is higher than the degree of the denominator, then we have no horizontal asymptote. However, we're going to split that up into a couple of cases, one of which we will handle in more detail in a little bit. So, the horizontal asymptotes of the function f of x, which is a rational function with the numerator p of x, denominator q of x. So we have four cases. So case 1, if the degree of q of x is greater than the degree of p of x, then f has a horizontal asymptote, which I will abbreviate as HA. It has a horizontal asymptote of y equals 0. Case 2, if the degree of q of x is equal to the degree of p of x, then f has a horizontal asymptote of y equals, I'll say a over b, where a is the leading coefficient of p and b is the leading coefficient of q. Now, the other cases where the degree of the numerator is higher than the degree of the denominator, we're going to break up into two. So the first is if the degree of p of x is exactly equal to the degree of q of x plus 1. So if the degree of the numerator is exactly 1 more than the degree of the denominator, then f has a slant asymptote, or oblique asymptote. In particular, it does not have a horizontal asymptote, and we're going to come back and look at slant asymptotes a little bit later. And then case 4, if the degree of p of x is greater even than the degree of q of x plus 1, then f has no horizontal or oblique asymptote. So these are the four cases. The nice thing about the horizontal asymptotes is that when a horizontal asymptote exists, you can tell what it is immediately just by looking at the rational function written in its standard form. Vertical asymptotes require a little bit more work, and then slant and oblique asymptotes require a little bit, or slant and oblique asymptotes are the same thing. They require a little bit more work, which we will address a little bit later. So now let's do a couple of examples where we look at a rational function and identify its vertical and horizontal asymptotes. Let's find the horizontal asymptotes and vertical asymptotes of the following functions. And let's look at a few of them. So first, let's look at the function f of x equals x squared minus 4 over x squared plus 7x plus 12. This is the one that we looked at the beginning, and we factored it in the following way. The numerator is x plus 2 times x minus 2. The denominator is x plus 3 times x plus 4. So let's go for the vertical asymptotes first. So we factor the numerator and denominator, and we have to check to see whether we have any cancellation, whether there are any factors in common between numerator and denominator. In this case, there aren't, and so that means that each one of the factors in the denominator generates a vertical asymptote for us. So our vertical asymptotes become x equals -3 and x equals -4. So these are the numbers that you would plug into these different factors in order to make them equal to 0. The vertical asymptotes, remember, correspond to the places where the denominator becomes 0 after you've reduced the fraction. Now, for the horizontal asymptote, we look at the original function and we compare the degrees. Now, the degree of the numerator of this function is 2, and the degree of the denominator of this function is 2, and therefore the horizontal asymptote is going to be y equals the ratio of the two leading coefficients. Now, in this case, both the numerator and denominator have a leading coefficient of 1, which means that the horizontal asymptote is the line y equals 1 over 1, which of course is just the line y equals 1. So if we were to graph this out, there's more that we could do with it, but for the moment we're going to leave it here. We know that we've got a horizontal asymptote at y equals 1, and we have vertical asymptotes at -3, at -3 and at -4. So those are, and I just realized that I put those one space too far over. Oh, that didn't help. There we go. So that's what our asymptotes look like. Now, we can actually go from here to fill in some other points on the graph to get a pretty good idea of what this looks like. So from before, we knew that this function has zeros at -2 and +2. So we know that the graph has zeros here and here. Now, at this point, we still we can make a guess as to what this graph looks like. So we know that when we're way off to the right of this function, then the function's going to have to be close to this line y equals 1. Now, typically, you want to try to sketch the graph in as simple a way as possible. That usually gets you closest to the truth. So we would be close to the asymptote y equals 1 when we're far off to the right, but then we'd come down, we'd pass through our 0 and pass through our 0 here. Notice that both of the zeros in the numerator have multiplicity 1 because analyzing the multiplicity of zeros of a rational function is the same as for a polynomial. You're just looking at the factors in the numerator. And now we know that this graph has an asymptote here at x equals -3. Let me try and do that a little better, which means it's going to go off towards 0 there. Now, figuring out what happens next, we can remember the facts that we had about looking at the denominator. Each of these vertical asymptotes comes from one of the factors in the denominator, and the behavior of the function near the asymptote is determined by essentially the multiplicity of that factor in the denominator. So this asymptote x equals -3 is coming from the factor x plus 3 in the denominator, which has a multiplicity of 1. Now 1 is odd, which means that near the asymptote the function behaves opposite. So since it goes off towards positive infinity on the right side of the asymptote, it's going to be going down towards negative infinity on the left side of the asymptote. All right, now figuring out what we do from here, we can use the fact that we know that this graph, where we're sort of building this from right to left, has to either go off towards positive infinity or negative infinity at the asymptote x equals -4. Now, if it were to go off towards positive infinity like this, we have a problem because we will have then crossed the x-axis again. This is basically the intermediate value theorem, that we would get a 0 there. But we can't. We know that the only zeros of the function are at 2 and -2, and we've already gone through both of those. So that can't be the case. So the graph must come back down and go towards negative infinity on this on the right side of the asymptote x equals -4. Finally, because the asymptote x equals -4 comes from this factor with a multiplicity of 1, that means that the function behaves in the opposite way on the other side of the asymptote, and so we get this. So we're able to graph this function that we started with, at least to get a good picture of it. Oh, and I missed one point that we do have here. Remember that we had the y-intercept was 0, -1/3, and so that matches up with the figure that we've got. And so that's a basic example about how you would sketch the graph of a rational function. Let's look at another one. Let's look at f of x equals x plus 2 over 2x squared minus 2x minus 12. The first step, as always, is to factor. So we get x plus 2, and then we can factor 2 out of this denominator, get x squared minus x minus 6. We continue factoring, get x plus 2 over 2 times x plus 3, x minus 3, and x plus 2. And there's our factored form of f. Now, at this point, we would stop if we're just figuring out the domain, or if we were asked for the domain, which we weren't in this case, but if we were, we would have to stop here before doing any reducing. And so in this case, we can see that our domain is all values of x, where x is not equal to 3 and not equal to -2, because those are the two values of x that would give us a 0 in the denominator. But now, when we reduce, we get to the rational function 1 over 2 times x minus 3. Because that factor of x plus 2 in the numerator and denominator basically canceled. So now this x minus 3 is going to give us our vertical asymptote. So the vertical asymptote of this function is x equals 3. So it's important that to note that in many cases, the domain, or rather the values of x that aren't in the domain and the values of x where the asymptotes are the same. In many cases they are, but sometimes they're not. Notice in this case, the number -2 is not in the domain of f, but we don't have an asymptote at -2. In the next video, we'll talk about how we can identify what is actually going on there. But for now, we're just finding the asymptotes. So we have a vertical asymptote at x equals 3. And then for the horizontal asymptote, we go and compare the degrees of the numerator and denominator. So in this case, the numerator has degree 1, the denominator has degree 2. When the denominator has greater degree, that means that we have a horizontal asymptote of simply y equals 0. One way I like to think about this is that when we're looking at a fraction, if the denominator gets bigger, that makes the whole fraction get smaller. Whereas if the numerator gets bigger, that makes the whole fraction get bigger. And so when we're looking at a rational function, we have a variable expression in the numerator and denominator. And when we're talking about horizontal asymptotes, we're talking about what happens when x gets really, really big. And that's going to make the numerator and denominator really, really big usually. So you've got the numerator, which is trying its hardest to make the whole fraction big. And you've got the denominator, which is trying its hardest to make the whole fraction small. And so the question is, who wins? Well, the relative strength of the polynomials in this context is given by their degree. And so when the denominator has greater degree, that means that the part of the fraction that's trying to make the whole fraction smaller is stronger. It wins, and so it sends the whole fraction very, very small. On the other hand, if the two fractions are equally matched, then they sort of balance each other out. They don't go down to 0, but they don't go off towards infinity. They balance out, like in our first example here. And if the numerator has higher degree, then it wins and sends the values of the function off towards infinity or negative infinity. So there we have the vertical and horizontal asymptotes of this function. Let's do another example. Let's look at f of x equals 6x cubed plus 3x squared over 2x cubed plus 4x squared minus 6x. Now here we can factor, and out of the top we can factor a 3x squared, be left with 2x plus 1. And the denominator will start by factoring out a 2x. That'll leave us with x squared plus 2x minus 3. We can factor this further to get 3x squared times 2x plus 1 over 2x times x plus 3 and x minus 1. Now, once again, if we want the domain, we need to stop here before we reduce. And the domain is going to be all values of x other than 0, -3, and 1, coming from the 3 factors of the denominator. Well, now we reduce, and we see that we've got a single common factor. The x in the denominator can cancel with one of the x's in the numerator, and we're left with 3x times 2x plus 1 over 2 times x plus 3 times x minus 1. Each of these factors in the reduced denominator give us a vertical asymptote. So that tells us that the vertical asymptotes of this function occur at x equals -3 and x equals 1. Now for the horizontal asymptote, we look back at the original function, compare degrees. In this case, we see that the 2 degrees are the same. They're both 3. And so the horizontal asymptote is given by y equals, and then we take the ratio of the leading coefficients. So the 6 is the leading coefficient in the numerator, 2 is the leading coefficient in the denominator, and so the horizontal asymptote is given by y equals 6 over 2, which is 3. All right, and then finally, let's look at the function f of x equals 7x to the 5th plus 1 over x to the 4th plus 2. Now this one isn't going to factor. We don't have a good way of factoring either the numerator or denominator in this case. So we'll go on. And if we want to know about the vertical asymptotes, then we want to know where the denominator is 0. So to find the vertical asymptotes, we'll take the denominator, x to the fourth plus 2, set it equal to 0. From there we get x to the fourth equals negative 2. And so x has to equal plus or minus the fourth root of negative 2. But this has no real solutions, because we can't take an even root of a negative number. So that tells us that we have no vertical asymptotes. Okay, so this is one of our functions that simply doesn't have any vertical asymptotes. For the horizontal asymptotes, we look at the powers, and we've got a 5 and a 4. And in this case, the power of the numerator, the degree of the numerator is greater than the degree of the denominator, which means that we have no horizontal asymptotes. So this is an example of a rational function with no vertical or horizontal asymptotes. They do show up sometimes. They give us a little bit less to work with than many other functions, but they are ones that do show up occasionally. Now, it turns out this function does have a slant asymptote. However, we're going to wait to talk about those until the next lecture, when we will talk about slant asymptotes, and we'll discuss a little bit more about what exactly is happening when we go through this reduction process and cancel out these factors. How does that reflect on the graph itself? And we'll put it all together and graph some of these functions with all the information